Assalamu alaikum warahmatullah. So today we are going to start the series of research paper explanation. So what will I do is I will go through my papers and mainly 4 papers, 4 journal papers, this one and this one and this one and also this one, not 4 actually, 6 research papers. I will explain one by one to for you to better understand. So today we are going to explain the paper about permittivity sensing of solid material and pH sensing applications. So mainly it is about liquid sensor. So we will show you what are the things that we have done in the paper and explain you how we can do it in the simulation. And there are some topics that might be better explained in simulation, and also some topics that are better explained in experimental setup. But as we don't have or we cannot show you every details of how we can do the measurement, because that will need you various materials like VNA and other tools. So it is not generally available. If you are already working in a well-established lab, then it is available for you. Otherwise, if you don't have access to those kind of material or those kind of equipments, how you can do the thing in the simulation, I will be explaining it to you. So the paper we have selected today is the permittivity or permeability measurement paper. So let's see the paper. It was published in Sensors and Actuator in Physics. This one is one of my early papers. So you can see the paper have those highlighted applications. Main focus, we have given main focus in pH level detection, and those are abstracts and graphical abstracts and some measurement in measurement environmental illustration. This is the introduction. I will show you a earlier version of this paper because this is not an open source or open access paper, so I cannot really show you the main whole literature or whole paper. So what I will do is I will show you a draft that I was preparing for before publication, and I will explain the result from that paper. So let's go and see the paper. Okay. So here you can see it is a earlier version of that paper. This is the introduction. If you find it interesting, read through it. We will just go to the design parameters and the experimental setups and so on. So this is the final metamaterial setup, metamaterial structure, and this is a fabricated result of that metamaterial. This is a 4x4 array of this metamaterial, and this is the simulation setup. This coin is here for comparison of the size, and this is the metamaterial characteristics or resonating characteristics of the sensor and the metamaterial. So this is the permittivity and permeability graphs. We will show you how to generate these graphs in CST. And this is a parameter swapping graph where I change the value of this split gap to see the effect of the length of this gap. And later on, I will show you the E field and H field. That means electric field and magnetic field. After that, this paper starts to working with measurement setups, but we cannot really do the measurement here. So what I will do, I'll show you that how you can get this result in the simulation, and also I will try to show you the here the pH values and the value how you can send how you can experiment the pH value. I will not show, once again, I will not show any measurement. I will just show you how you can see the simulation setup. And this is just an explanation of the paper, so I'm not going to explain every details how I designed this metamaterial. I am expecting you to be able to design a metamaterial from this description. All the necessary description if you need to design this metamaterial in CST is available in this paper. So if you want to remake this metamaterial design, you can do it by yourself from following these parameters. Okay, so let's go to the CST. We are using CST because I'm more comfortable, and I think this is a very user-friendly tool for microwave application. So this is the design of that metamaterial. Here you can see that those are components, and in components, this one is the substrate, and it is substrate in FR4. I think, yeah, we already mentioned this one, and the thickness is here. So let's see if thickness is okay. Cannot okay. So I copied this shape. I think let's see from here. So yeah, it is about the same size. Okay. So for the sake of your understanding, I will just sweep through the designing process. Then I'll show you how you can get the result and how you can prepare the um, sensing setup. So let's open. Let's delete hide this structure. So now we are going to start making a new design. So first, so far we have designed everything except the splitting gap. If you see here, we haven't done this splitting gap yet. So the gap is 0.5, right? Okay. So we have to make a gap. So as you can see, G2. Uh, Here we will use parameter sub because later on I will show you the effect of this. We are showing this the effect of the length of this gap. That's why we need to change the value of G2. If you see that we in our simulation we simulated the result for from 2 millimeter to 0.5 millimeter. So let me show you how the gap affects the metamaterial performance. To do that, we have to create a parameter, give a parameter as G. Then we will change its value using parameter swap and run a parametrical swap simulation. we are using the initial value of 0.5. 0.5. So we will run the simulation for from 0.5 to 2 millimeter. Okay. So for our metamaterial design is ready. Now for getting the experimental result, and just start simulation, and then it will give you the simulation result. I have already simulated the setup for your convenience. Let me show you that after simulating this one. Um, okay, let me show you the boundary condition first. So for simulating, we should go to the simulation and then assign the frequencies. It is 1 from 20. You don't need 20 because we are just recreating the sensor, so we can just from start from 10 to 15 is okay. So let's give 10 and then 15. We okay. Okay, and then the boundary conditions. Here, boundary condition, we if we want to show the result for TE and TM mode, then I mean, first of all, the boundary setup is okay here. We have all around uh, unit cells all around, and then open add space for wave propagation. For more detailed boundary view, we should go to the fluctuate boundary ports and see as we will simulate in TE and TE mode also. So we will need two ports. So we used two ports in JMini and JMax, two ports. Okay. So why? Because port 1 will give us the TE mode, the result of TE mode, and port 2 will give us the TM mode's result. Okay. I think so far everything is done. First, run the simulation once by clicking going home and start simulation. I will not do this thing. Okay, I forgot about another thing. For E field and H field, we have to set field monitors. Okay. For setting field monitors, let's go to field monitors, field source first. Sorry, field monitors. Sorry, we should go to the field monitors. So actually, we should first run the simulation once and see the result. First this one, then when you see the metamaterial is resonating at 2 point, let's say 2.3 or 2.2 gigahertz, then you should come here and say we need a parameter, we need a H field in 2.2 or something. Okay, okay, let's create them for 2.2. Let's say this metamaterial is resonating at 2.2. Okay. Actually, I designed this sensor to show you. That's why let's make another new component, whatever the name is. Okay. Just bring them here and show. Okay. So now we can see our previous design and our new design. So you can see those two designs are identical. This one is the new one and this one is the old one. So you can for just to show you how to make the design, I did this thing. So now we don't need the old design anymore. So I'm deleting the old one. Okay. So I will simulate this uh, sensor now. Let's start simulation. Okay, so we have completed the simulation. Here you can see the S11 and S21 result is here. So you see X max, and this is max 1 max 1. What does it mean? It means from port 1 on the max side to port 1 on the max side, kind of like uh, S11. Okay, this one is S11, and this one is see, this is the co this one is cross polarization, this one is copolarization. That means this one is the port 2, port set 2. Remember, if you remember that we used two sets of port, right? Here we use two port. So this one means S11 for this port, and this one, this 2 means the second port. Okay. Okay. So what does it mean? It means that this is S11 TE at TE mode. Let me see them. Yeah, sorry. This one is S11 for TE mode, and this one is cross polarization. That means from one TM mode port to another TE mode port. So cross polarization, if you understand the basic of concept of cross polarization, you will understand what I'm saying. So this is S21. Mini means the backside port of the backside port at the backside, and max means the port and the at the front side. Let me show you again. Uh, this one is the X max at the front, and at the back this is X mini. So this one is S21, and this one is again S21 in cross polarization. This one is S11 from the back side at cross polarization. So rest is the same thing. So this is the result for S11, and this is the result for S21. As you can see, this is similar to the paper. Okay. So now we can extract the material properties from this one. To extract the result, you have to go post-processing and then result template. So from post-processing template, you should go to S parameters from here, and then select extract permittivity and permeability from S parameters. Now it will ask you for material thickness. It is the thickness of your substance. So in our case, it was 1.6. So let's click that and click eval. You see that there is a new template will generate, and if you click evaluate, there will be a new table under the table section. Here you can see that material properties are shown here. So this is your epsilon, means permittivity, and this one is permeability. So as you can see, I think let me find the paper again. Okay. So here you can see that we have permittivity and permeability graph. This one is shown in real and imaginary. So to show real and imaginary version, you need to go to here and click real and imaginary. So you can see that this is real and imaginary. It shows kind of different them and then the one in the paper. The reason is we have to change the values. So let's give it 10 by 10. 10 by 10. It is the 10 now. Now see the structure is more similar to the paper. This is permittivity and permittivity. So the red one is real, and the black one is the black one is the real, and the red is imaginary. Here the below dot one is imaginary, and the straight line is real value. Similarly for permeability, you should go to the mu and then click real and imaginary. Here you can see that this graph is pretty much the same graph from here. Okay, it will change time to time, like one simulation to another. The reason is sometimes meshing is different, sometimes the conditions are a little bit different, but it should not make a huge difference. Okay, so now we will go to the, I'll show you the parameter swapping simulation later on. But before that, let me show you the E field and H field and surface current, how to generate these things. Okay, first you need to know which frequency, at which frequency this metamaterial is working, or at which frequency you want to show the E field and H field. In our case, in this paper, I showed for 12.17 gigahertz because this was the resonating frequency of the sensor of the metamaterial. Okay, so let's go to our graph. So here we will generate E field at the lowest point of S21, so it is 12.15. Okay, so now let's go to simulation, field monitor, and here you can see that you can generate E field, H field, and surface current, all that for a specific frequency. You can also show steps, or like you can also set a value that from which frequency to which frequency and which interval, things like that. You will explain or explore it by yourself. I am just showing you for my scenario. Okay, so as you can see, we'll go for 1.5. Okay, so let's click apply. We have created a E field monitor. Now we will create the H field for the same frequency, apply, and then surface current for the same frequency. Okay, so here you can see there are 3 monitors have been produced, and now we will go to home and start simulation. So you can disable, if we click disable, then this result will be present there, and if you don't click continue, then the simulation will run from the beginning, and it will take much longer. As we are just creating one frequency, so I did not did the whole thing. I just created for that specific frequency. Okay, so the simulation is completed. Now we will go to E field and H field. Here you can see that E field shown in this photo, but it's bit different. So what we should do, we should go and select contour here. Now you can see the structure is showing more meaningfully. Okay, so you scale it down as you like, but you should maintain same scale for every image in your single paper. Okay, so you can see that this was pretty much the same, and we have also shown the scaling for this figure. It is almost the same. I think 11.3, right? Okay, so let's make it 11.3. Okay, this is E field, and let's go for H field. Okay, for H field, the scale was 21 almost, I think. So yeah, for 21, this is similar. And for surface current, let's go to surface current and see the surface current. Here we can see that this graph is different. So now we need the arrows. Okay, so here is the arrow. So to make it a bit more appealing to the eye, we should make some changes, like we can decrease the density, we can minimize, increase the minimum size to appear them a bit larger. We can also make them a little bit bigger. If you zoom in and out, you can pretty much do whatever you like, how you want to present the pictures. Okay. And You can also change the positions by changing the phases. It is totally up to you, but you should mention everything you do in the paper. Okay, so far we have done up to this point. Now I will show you the steps for creating a parameters for this gap. Okay, actually, if I start changing the structures here, I'll lose those results. So, do we need any results of that? Not any result. Okay. So I have shown you these results. So if I change any parameter, these results will be gone. So now I think we don't need them. So let's start changing some things. Okay. So let's see here. Go to the parameter swap and create new swap and then new assign new parameters. Let's check actually how many parameters have we have GG. Okay, for the sake of our understanding, I call it G2 because in our paper we used this G2. Okay, so let's go back to the design and this is 7. Ah, let's give it G2. G2, G2. Okay, so now we have given this gap as a assigned this gap a parameter, and the parameter is G2. So now if we change the G2, the gap between these two resonators will change. So now let's make a new parameter and say G2 from what was in the paper. The paper used from 0.5 to 2. Okay, so let's say 2 from 0.5 to 2. A number of sample is simple 1, 2, 3, 4. So 1, 2, 3, 4. Okay, let's check is it okay or not. Oh, so here you can see the gap is changing. So now if we click start, the simulation will run 4 times for these 4 values. I will not do this here because it will take so much long time. I am just showing you how the process has been done, and I have already done this simulation in another project. So let me show you that one. This is the same design. We have already run the parameter swap. So let me show you the result. After completing the simulation, oh, okay, sorry, I think I have to reopen that again. Maybe this one, right? Or this one. I forgot. I think this one. Okay, yeah. So yeah, I have already completed the parameters of simulation. In the simulation, this we continued from 2 to not 0, but 0. I mean, not only 0.5 up to 0. Actually, it is the same. I think in our this initial manuscript there was a mistake. It should have been from 0 to 0.5 because you can see figure we did from 0 to 2. Okay, so here you can see we have same thing to 1.5 1 0 0.5. It's okay, you can just change the simulation values. It doesn't matter which sequence they are appearing. Okay. So here you can see this figure is almost like the similar figure for this one. For G, there was G0, the peak was in here, and for G2, the peak was in here. I think there is also another mistake. It's G1, but in actual scenario, we used G2. This is the earlier stage, earlier manuscript, so that's why these mistakes are here. So for 0, this point, and for 0.5, this one is this one, this one, and for 2 it should be here, for 2 it is here. So the things have shown a linear change. Okay, let's go back to our design, and I will show you how you can do this sensor setup for sandwich model. I think I have already explained you in an earlier video uh, that how we can make a sandwich structure, what is a sandwich sensing setup. So if you don't understand the concept, you can see how we can make a sandwich kind of. It's general practice to call sandwich. You can call it whatever you feel like. So you can see the setup for sandwich modeling or sandwich setting, sensing. So how do you do that? Is, let's say we are sensing Roger 3010. Okay. Uh, we go to the modeling section again, and then we design something. Okay. So here you can see that everything is same, except we need to uh, assign the values, I mean assign the material on top of the metamaterial itself. Now it is on top of the metamaterial. And why I started from 0.5, not 0, because I there is the copper layer. This copper layer has a height of 0.35 millimeter. So if I didn't use this one, just started, if I just started from 0, this material will overlap the position on the overlap with the copper. So it will be theoretically wrong, because in general case you will not be able to put the metamaterial and the testing object in the same place. You will be putting it on top of the coppers. Okay, so I give the value, and here you can assign Roger RO30, I think 3010. Okay, 3010. Yeah, you can just load and apply. So now we have the sandwich model. We can, if we run the simulation, and you will see that the S parameter, I mean the result, this value have been shifted, like here. The resonating frequency uh, will change. Similar, this frequency will shift and come in this position. So similarly for the other steps, you can assign new material for what I did for F4. Let's assign F4, edit material, assign material and color, FR4. Okay, so this is now FR4. If you can see that this is FR4. Okay, so this is one process. You assign one material and then run the simulation, collect the result, and then assign another material and then collect the result. There is also another way to do it. I think this is more easy by using the parameter swap. What you should do is click here and assign a custom mid material. Go to new material, and here you can see that you have the option to change the permittivity value. Actually, those value can be changed as well, but it will not make that much difference because we are mainly focusing on dielectric properties. So as this sensor is a dielectric sensor, so for now, for the simulation, for the sake of simplicity of the simulation, we will only consider the permittivity. Okay, so we will assign a parameter or a variable here. Let's call it. Okay, now this one is ready. Okay, so now what we will do, we will go to parameter swap and create a new sequence and then change the value of IP. Instead of linear swap, we will make arbitrary points so that we can specify which value we want. So then we want to run the simulation for 4.3. So here you can see how we should write. You should use semicolon and then semicolon, then 4.3, right? 4.3 and then 3.66. So semicolon 3.66 semicolon 2.2, right? 2.2. Okay. So now if you click start, then the simulation will run for the 4 arbitrary values and you will get a result similar to the one. For value. Okay. This one is the parameter swap. So I mean the process is the same. If you run the simulation, you will get instead of G4 with the value for G, you will get the value for EP and the permittivity and permeability. Permeability for the resonative frequency for different level of permeability and permeability. So I think you get the concept for this one and these two simulations. I will not show you, I cannot show you the measurement setups because this is not what you can do without a lab. So I will skip this measurement step. You have to get access to a lab, then you may be able to do the measurement. For pH sensor, what I did is I changed the structure into a transmission line based metamaterial sensor setup. Here it was only a array of sensor, array of metamaterial, but later on for liquid sensing, I use a transmission line based sensor. To do that, what we did is let's delete this solid. Okay, first, okay, you can see there are 1, 2, 3, 4, 4x4 structure. Okay, let's copy this structure 4x4. How we can do that is select the component and then transform and click copy and then just move it like this. You can do it one by one, hit apply, then if this one is done, then make another one here, make another one, copy here. This also okay, but another easy way is to use this factor. So here you can see that it is automatically have been designed 3 times. Okay, so now click apply. So you have an array of the components. It's a very big, long, a very long list of array, but you'll get even more. Okay, so again copy and apply 3 and yeah. Okay. So now you have a 4x4 array. For the simplicity view, you can select all the FR4, I think all the, yep, and then just add them into one substrate. So now this material has one substrate and 4x4, I mean 16 resonators. Okay, so now Actually, I'm designing it here, but we cannot simulate the metamaterial transmission line based setup in here because this is a metamaterial setup. We need to go to the setup for antenna, and if you want to refresh your memory about how you can set up the metamaterial simulation setup or transmission line, you'll find in my channel there is another video which do the same thing. Okay, for now I will show you how you can do that. Just pick a new project, and so now I'll copy everything and paste it here. Now we have structure. So now, as you can see in our paper, that there is a transmission line. So let's make the transmission line. I think somewhere I have mentioned the size or the length width of this material transmission line. I forgot for now. So let's make it by ourselves. Okay. Remember, I'm just showing you. So you need to calculate the length and width of the transmission line in CST by yourself, because your simulation may be different, your substitute size may be different. So the transmission line is ready, and now I will assign ports. Go to simulation. I will use discrete ports. Click this corner and the substrate corner. And so this is the port, and it means shall also. So up to you. Apply. We will need a second port. So from this point to this point, and then even this one. Okay. So now we are ready for the simulation. For the sensor setup is ready for simulation, for sensing simulation. Okay. Now what we have to do, we have to set up this audio. I mean the liquid channel. So the liquid channel, you can see perpendicular to the transmission line. You can do actually two things. You can make a pipe kind of thing. I will show. Okay, let me show you another project. I have done the pipe setup. Okay. Okay. Here you can see there is a, I have made a cylindrical pipe, and then the one shape is transparent. Yep. Sure. Okay. So here you can see I have first designed a plane similar to this type, same material properties, and inside that pipeline I've used water. Why there is this cut? Because actually there is layer of water. This paper has a different application. That's why this is like two layer of water. And I will show you how to make this kind of cylindrical shape in this paper explanation video. But for today, I will just give you an example. But I will not show you any. I make the pipeline. Okay. For that one, let's make a layer of layer of polymer. What is this? This will be the layer of plastic pipe. X is okay, and Y, let's make it 5. Okay. Height 3. I think polycarbonate. Okay. For my advice is find the property of a plus of plastic, then give the value epsilon value here. Let's go with polycarbonate. Okay, let's do the preview. So this is the, and on top of this layer we will make a liquid layer. Okay. 0.035 plus 0.25, right, for plastic layer. Okay. And here plus we will use a 0.5 millimeter thick of water layer. Up, sorry. So yeah, here is the water layer. So why I did this plastic layer really, because water is mostly conductive. If you put the water on top of the copper directly in the simulation, it will connect the resonator gaps and it will show wrong simulation result. And also in the measure, you don't put the water directly on top of the metamaterial sensor, you use a channel. So to replicate this video, we make a simulation based layer, plastic layer, and then we put a liquid layer. Okay. This is how you do the simulation, do the experiment in the simple. And what you have to do now is go to the water layer, I think this one, and assign, sorry, instead of using this value, assign, collect different value of dielectric constant from for different pH level. You can find it in many papers. They will show you that for this level of pH value, what is the dielectric property of that of water, and get the value from those papers and then then assign them in the material. So assign a new material, water, 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 EP, epsilon. Okay. Apply. Let's give a value like 78 for now. I'll make it transparent so it will look like water. So now we have a sensing setup with on liquid channel. And now we can change the value for different pH level. We have to design different dielectric properties and run a parameter swapping simulation so that we can see the effect of different permittivity in another word, different pH level. But you have to get the permittivity or the epsilon value for different pH levels. In our case, we did not use this because we use actual liquid with different permittivity, different pH value, pH levels, and we actually use actual solutions. So what we did, we we made the solutions and then examine the pH value by pH meter and using those solutions, and then we use a VNA to measure the effect. But for your case, my suggestion is you should also, if you are using a VNA, you should also get the dielectric values using dielectric proofs for different pH levels and use them in the paper. So far this is what we have done, and you can do that thing in the simulation. I showed you how you can do that in the simulation and to achieve the results. Those results will be similar to the paper that I have shown you. And to get the value from CST into Excel file or like any other graphing software, you need to extract the value. To do that, you need to go to post processing and then import and export. Go to plot data and then give it a name. For my case, I give G. It is a different value of G4, so I give it a G values. Okay, so here you can see first row is the frequency ranges and the second one is the S21 values. You have to think S21 value is in dB or not. Be careful about that. So far everything in this paper is have been shown, and you can use any other software like Excel or Origin Pro to plot the graphs like this. So in the next videos, I will be showing another paper, maybe I think this one for soil moisture, and then the this one. So hopefully I will see you in the next video. Thank you for giving your time and hoping that this video will help you inshallah. So have a good time. Assalamu alaikum warahmatullah.